A buffer is a mixture of two things: a weak acid, or base, and a salt that has an ion in common with the weak. Buffered solutions maintain a relatively constant pH with the addition of strong acid or base, at least until the buffer capacity is reached. They can do this because, between the weak and the salt, one is ready to behave like an acid, the other like a base. So whether we try to raise or lower the pH, the buffered system is equipped to resist the pH change we try to make. The pH of a buffered solution depends on two factors: the Kx of the weak, that is the Ka or the Kb. If it's a weak acid, we use Ka. If it's a weak base, we use Kb. And secondly, the ratio of the weak and common ion concentrations. The pH does not depend on the absolute amounts of weak and salt, only relative amounts. In other words, it's not the number of moles of weak or the number of moles of common ion from the salt. It's the ratio of those two that determines the pH. The moles of weak and the moles of salt affect the buffer capacity, which is how much acid or how much base could be added to this buffered solution before the pH changes appreciably. But the pH only depends on the relative amounts of weak and salt. Specifically, if the weak and the common ion concentrations are the same, then the pH is equal to the pKa of the acid. Or, if it's a weak base, the pOH is equal to the pKb. If the weak concentration is greater than the common ion concentration, then the pH tips towards the weak. If the weak concentration is less than the common ion concentration, then the pH tips towards the ion. If you're feeling a little bit like this guy, let's show you this with an example. Nitrous acid has a Ka of 7.2 times 10 to the negative fourth. When a buffer has equal concentrations of nitrous acid and nitrite ion from, say, sodium nitrite, find the mixture's pH. Since the weak and the common ion have the same concentration, the pH of this mixture will be equal to the pKa of the acid. We can find the pKa by taking the negative log of the Ka, and that comes out to be 3.14, not related to pi. This fact will remain true no matter what the concentrations of the nitrous acid and the nitrite ion, as long as they're the same. If the nitrous acid and the nitrite ion are both 0.1 molar, the pH will be 3.14. If they're both 0.5 molar, the pH will equal the pKa of the weak, 3.14. If they're both 1.25 molar, the pH will be 3.14. Suppose, in a different case, that you have a buffered system, but the nitrous acid solution concentration is somewhat higher than the nitrite ion concentration. The pH will tip toward the one that there's more of. In other words, it'll tip towards the acidic range. So we would expect a pH to be somewhat lower than 3.14 because there's more acid than there is base. The nitrite ion acts as a base, so if there's more acid, the pH is going to be somewhat lower, somewhat more acidic than 3.14. On the other hand, if there's a higher concentration of nitrite ion than there is of nitrous acid, then the pH will tip towards the ion. Here, the ion is the base. The nitrite ion accepts protons, so we would expect the pH to be a bit higher than 3.14.